Hi, I'm Debra Fischer, and I'm a professor at Yale University in the Department of Astronomy. I am currently the PI of an instrument called EXPRES, the EXtreme PREcision Spectrograph, which was recently commissioned at the Lowell Discovery Telescope near Flagstaff, Arizona. I've also been the PI for two other instruments, CHIRON, which is a spectrograph in Chile, and the VUES spectrograph, which is in Lithuania. I became interested in instrumentation when I realized that to improve our precision, we needed to build better instruments. It was clear in 2003 that the HARPS spectrograph, which was environmentally stabilized, was producing much better measurement precision. My hope early on was that there were some small tweaks that we could make. So I started working with fiber scrambling, but it quickly became apparent that there were many contributions to the radial velocity error term, and just driving down one of those terms was not going to move us along the path to 10 centimeter per second precision. The qualities that I think are important for success in instrumentation projects are a sense of optimism and just incredible persistence and attention to detail, and also the ability to kind of think outside the box and reimagine how instruments could be. Balancing risk and novelty is one of the biggest challenges in developing a new instrument. If you build another instrument that is the same as the last instrument, you would be foolish to expect that you're going to do any better. So it takes a lot of thought and care and many simulations and attention to detail and an understanding of the end-to-end process. I started thinking about instrumentation in 1999. It looked like the radial velocity precision had plateaued at about 3 meters per second. And I wondered if we could drive our precision to 1 meter per second, which was almost heresy at the time. And the reason is that everyone felt that the radial velocity precision was limited by the stellar activity, the velocity flows from the surface of the star. If that's true, then what's the point of building an instrument that delivers higher fidelity data? You're always going to be limited by the photospheric noise, the photospheric velocities. My belief was that if we could build an instrument that delivered higher fidelity data so that we were sure that we were zeroing out the instrumental contributions to our measurement precision, then we'd have some hope of finally being able to disentangle the velocities from the surface of the star from the orbital velocities. But until we built that instrument, there was just no point in even talking about it. For me, it was incredibly important to see HARPS achieving 1 meter per second precision, and understanding that that was a bar that astronomers thought was too high, could not be met. And yet, the Geneva team did this by controlling the instrumental precision. And as a result, some of the velocity jitter that had been attributed to the star went away. So what if you build an instrument that can deliver, 10 centimeter per second precision? Will you be able to do better? And I would say I never really knew what the answer to that question was going to be, but I always felt that it was an important enough question and that the payoff was going to be large enough that it was worth the time I spent in my career pushing to this point. I would say all along the way, I felt a lot of pushback from the community who continued to say that the radial velocity precision is limited by the stellar noise in the star. And that was a hard thing to push back against. One of the biggest challenges that we had was with EXPRES. We designed an instrument that was higher resolution because our simulations showed that it would be easier to disentangle the photospheric velocities from the orbital velocities with higher precision, better resolved line profiles, high signal to noise. And then when we finally thought we had everything fixed, we observed our laser frequency comb for about an hour, and we saw the most beautiful sine wave, that you could imagine creating. Freezing out that noise source in every observation would have meant that we were introducing radial velocity scatter, which came from our wavelength calibration at the level of 3 to 5 meters per second. That was completely unacceptable. It was the genius of someone on my team, Andy Shemkowiak, who realized that this was probably a beat frequency, the laser frequency comb, and the vibrations in the cryocooler. And we reprogrammed the spatial light modulator, which flattens the flux from the laser frequency comb so that it ran at 55 hertz and eliminated the problem. I think the key lessons that I've learned are that there are so many things that can go wrong. I often say 100 things can go wrong. If we only get 99 of them right, it's not good enough. You can't just hammer down on one error term. You can't imagine that you'll improve the telluric model and suddenly everything will be okay. It really requires a holistic effort to push down every single term in your error budget so that you can ultimately improve the measurement precision on stars. I guess my advice for the Sagan summer workshop participants would be that instrumentation is incredibly rewarding and gratifying. I think it should be a component of the education for all graduate students, and your lives will be enriched and you will have a deeper understanding of your data if you at least get a chance to work a bit with instruments. Finally, I want to thank all of the amazing people, Colby Jurgensen, Andy Shemkowiak, Tyler McCracken, Dave Sawyer, Rebecca Stoll, amazing undergrads, Christopher Leet, Abby Mintz, Yonatan Zeff, who also helped to commission EXPRES in the early days when nothing was ever working. Graduate students, John Brewer is now a professor at San Francisco State, Lily Zhao, Ryan Blackman and Ryan Petersburg, and Joel Ong, Ellen Davis. And every good movie ends with bloopers, right? So here's our bloopers during the commissioning of EXPRES.
Colby, you're saying that like
What's wrong with you? Did you know how to ride a bike?
Actually, it's not clear to me that the pedals go around without hitting the ground.
I think they do. Let's get the front shot here. Let you go, Tyler.
I have this problem on these trips where we work hard all day and then somebody does something like this and we take pictures and then we mail the pictures home and everyone thinks we're goofing